All right, everyone. So I just wanted to make a quick recording to go over for your lab number 6 kinetics of a chemical reaction activity that you performed on, well, for this year, 2022 spring semester. It would have been, we're doing it on a Wednesday. Here's the answer to the pre-labs. All right, I'll also upload this document with commentary separately on the website for you all. And I'll put it in the Neo as well and the online agenda, okay? But what I've gone through is I basically did a giant color coordinated commentary on how to do this lab. So first of all, check your pre-lab answers and make any edits, okay? Remember to do a single line when correcting. So if you realize, oh, that wasn't the right answer, all right, simply cross out and put in the new answer. Do not scribble, right? Your pre-lab should be on the right side. Notice here for pre-lab, what it was really asking you to do is to basically perform rate 2 over rate 1, or your general first encounter with chemical kinetics practice problems performance that we did before. So you have data, you simply compare the difference between rates relative to the difference between a specific changing concentration of a reactant, and you calculate, okay? And then you find the exponent, all right, in order to determine its first or second order. So you should have gotten that for when looking at the change relative to iodide. All right, so I highlighted that in green, comparing trials 1 and 2 to figure out the reaction order that goes with iodide. You should have found it to be first order. You also should have found that for persulfate, which is S2O8, all right, you should have found that that is first order as well. All right, and I highlight the reaction trials that you want to use. And I'll 1 second, I forgot to add in here 1 and 3 to help you out. And then what you see is that's it. And then you would simply write the rate law based on this mechanism. And here's the thing, it asks you, could you figure out the rate constant and the rate law with only the chemical equation? And the answer is technically no, because rate law and specifically rate constant must be determined experimentally. So you'd have to do approximation methods, which is what you learned today in unit 5, day 4 lecture, but I'm not asking you to do that. So now let's get into the nitty gritty of it all, the analysis walkthrough. You're going to have the entire weekend, and this will be your only homework for the weekend, except for maybe one really short practice sheet. All right. But like, this is the chunk of the weekend, because in order to complete this lab report, you have to do a crap ton of math. All right. Pardon my French on the YouTube, but you got to do a lot. Good thing I selected not for kids. Ayo. So here's what you have to do. I'm so sorry, by the way, but you just have to do this. This is like AP life. You are going to work yourself through calculating the rate law and the rate constant for each experiment. Okay. And you did 7 experimental groups where you had 7 different focuses of change. All right. 7 different setups in your chemical reaction conditions. So what you got to do is, 1, here's what a sample batch of data might have looked like. All right. Notice you have trial 1, trial 2, and trial 3 for volume, where you found the average mass of a drop of water to see if you get it consistent. And then you average all of those. All right. Then you have time for each experimental group. All right. And for us, you have relative temperature. The temperature should be relatively the same, because you're basically applying whatever temperature one sample's at is true for all the rest of the samples. All right. So it'll be somewhere around room temperature. All right. And you're just going to kind of have one basic measurement and call it good. So notice here, you see that all the temperatures are the same, because this is all held at about room temperature. We did not do part 3 and 4 because we did not take a focus on activation energy calculations. That is Arrhenius equation and some other mathematical performances that I'm going to trust that you can self-study and you can figure out the math. Just a little bit of manipulation with equations known to you. We're really just focusing on rate law constant and rate law expression here. So part 1 is you first got to calculate the volume that goes with your average. Okay, so you calculate an average mass. You got to turn that mass of water into an average volume of water. So you do some basic dimensional analysis. Make sure to include the sample problem. It's not even one sample problem. It is like the sample problem. So include the, gee willikers, this pen, the steps for this calculation of volume. All right. So it's not even a sample. It's just like, you just got to show it. Okay. It's part of your analysis. And since there aren't other trials you're running, your one sample is your math, the entirety of it. Now here we get to part two. Part two, calculating the rate, has 4 parts to it to make it happen. So first, you need to know that you have to show a sample calculation for each part that you calculate. And then you have to create a table with a summary of all those calculations for each experimental group or each reactant, depending on the portion that you're calculating. So the first portion you're calculating is what you'll see here is this is completely just a walkthrough. This whole section right here is just a conceptual walkthrough of the math. So what you do is you take the volume calculated earlier, all right, and you figure out based on that how many, all right, how much solution of what is this one called? This chemical called? Hold on, let me double check my wording. You figure out this solution based on persulfate, because it's part of your oxyanion rules. Even I'm a little rough on them. So your persulfate, so you have to use your molar ratio between your reaction, your reaction, okay? Once you figure that out, knowing that you are using a 0.0010 molar solution of persulfate, sodium persulfate. By the way, you can trust that because this is from a lab kit from Flint Scientific. So the solutions are exact. All right. Then you take that molarity, you then use your reaction step 1, sequentially your reaction step 2 molar ratios, where I2, your intermediate of diatomic iodine, is used to translate between the two, okay, reactants of persulfate and bromate, I believe it's called bromate ion, to get the moles of bromate. Once you get the moles of bromate, then you calculate the change in bromate, all right? So that's a lot of words. Here's the actual process with numbers. So like I said, I'm going to download this for you guys so you can study it on your own with all my commentary, but it's relatively quote unquote simple calculations. Here's the catch. You got to track the units. Unit tracking is going to save you. Okay. So unit track. Once you get the moles of persulfate ions, you go to the next portion where you use your 2 sequential reaction steps and their molar ratios with your intermediate as the bridge between them in order to calculate the moles of bromate ion. Once you get your bromate ion moles, then you use the volume drops using the volume earlier that you found, right? This was found earlier, step 1, or I should say calculation 1. All right. Then you use this calculation. Oh, gee willikers, that was the wrong section. Right here. Then you use this from calculation 1. All right, in order to find the change in bromate, right? Because you're basically diluting it. So you're finding its molarity with respect to how much you diluted the sample. All right. And you have a really small sample. So you definitely shouldn't have a very strong molarity at all, right? You're using these tiny little microplates. Okay. So then you get the change in bromate ion molarity. But in order to find the rate, you need to do the change of bromate over time. That just got you molarity change. So then your actual final step in the sample calculation is here. For experiment group 1, you have a change using the time that you measured, the molarity that you just calculated, and then you divide the 2 and you get this value of 8.2 for my sample data. By my, I mean the chemistry kit sample data. 8.2 times 10 to the negative 8th molarity per second. This should give you a good gauge, by the way. Help you gauge and determine whether your values are correct. So use this as an approximate to judge your own values. All right. Now you can't lie about your data, but you can definitely note to self, hey, if this is super off, there probably was some error, right? And that you can talk about in your lab. Then you have to do this for every experimental group because we set up 7 different conditions. So you got to repeat that process, but do not show me the math. I only need the math for the first example, just to let me know that you know how to do it. Then you repeat this process, summarize it all in a table. We will be using this table for future calculations. Part 2 of writing the rate law is you need to then calculate the initial concentrations. Because remember, with experimental rate law calculations, you base it off of the initial rate for the initial concentration values. So you got to go through a really simple M1V1 equals M2V2, right? This should sound familiar for a diluted sample. You simply just have to calculate the molarity of, in this moment, the potassium iodide drops. This is what we're measuring here. And then you'll do it for your bromate drops and then for your acid drops. All right, so you have to do this calculation 7 times for each 3 of the reactants, which means you're doing 21 of these calculations, all right? Setting up a table with 21 values. Notice, these are a good judge for you to compare, right? Use this table to judge your own values with this table. All right. So that's what we have there. This should be pretty comfortable, just really tedious. All right. Next, we have part 3 of writing the rate law is once you figure out your rates, then you figure out your initial molarity, you need to figure out the rate order or the reaction order with respect to each reactant. So you got to do that rate 1 over rate 2 or rate 2 over rate 1. Honestly, the proportions will stay pretty similar. Okay. And hopefully it should look very familiar to you, but now you got to do it for each of the reactants. This right here, by the way, is just conceptual background. Skip over that and start looking at the math. So remember, when we're trying to calculate the reaction order with respect to an individual reactant, you basically can treat the other solutions as constant as long as you pick the trials where you actually held those other reactants concentrations constant. So what you see is I basically cancel out, gee willikers, I basically cancel out the concentration of bromide and H plus ion because they end up being the same for trials 1 and 2. And I simply just focus on the changing iodide ion, okay, iodine ion or iodide. All right. And I just do a basic calculation of proportions and I do the anti-log or the natural log to figure out what the exponent would be. And I find that, by the way, it should definitely be first order. You have to show your math for each one of these reaction orders with respect to each concentration of each of the 3 reactants. Thankfully, it's only one set of calculations, one set for each reactant iodide, one set for each reactant bromate, and then one set for each reactant of H plus ion. But then you're done. You don't have to do a whole table again. It's just it. So then you repeat the same process, this time focusing on a trial or an experimental group specifically that has only changing bromate, and then the other 2 are held constant. So iodide and H plus. So then you just treat them like constants, you cancel them out, and you can just focus on the isolating the bromate. Again, you do the anti-log, you find that this also should be first order, all right? The final one is your H plus, okay? You do the whole same process. Notice I'm getting all of these rate of reactions from the table that you calculated in 2A, part A. And you get that H plus should be second order. You should have calculations for all of this showing me that you actually use your own data. If your data did not show this, that's a lot of error that you can talk about. Okay, so now comes final part D, the actual rate constant that goes with your rate law. So you use your rate determining step, which is according to the background information on your packet, reaction 1. And I wrote reaction 1 over here for you, okay, for reference. Here's the reactants, here's the products, okay? You rearrange the rate law equation in order to isolate the K value, and then you simply choose one of those trials, right? Just like we did when we first started talking about rate, you use one of those trial rates, you use the pairing, the accompanying concentrations that go with that rate, that run or that trial, and you simply calculate the rate or the rate constant, which should stay the same no matter what you use, because your rate constant is supposed to be a consistent rate for that specific reaction despite the trial, right? Then you have to calculate the rate value, or sorry, the rate law constant for each experimental group. So don't forget, you have 7 experimental groups. So, and notice here, we do call it K prime because it's based off of estimations of RDS. So this would technically be K prime. I'm not going to dock you off for that, but do realize that that's why you see the prime there. So that's your homework for this weekend. Here's the thing, don't forget, I am uploading all of this commentary and this video for you on YouTube, on the Weebly website with the agenda, on the Neo, and of course on the Unit 5 outline. Best of luck, and sorry guys, but here's the plus side. Once you get into college and you have to maybe do this again, you'll know what to do. So yay, and if you were ever super like lacking confidence in your rate law mastery, you will get it. You will get it after this. So good luck. Bye.